So yeah, good evening, good afternoon, and good morning, everyone. My name is Cusicanqui. I am a postdoc researcher in Institute of Earth Science in Grenoble. I am founded by the French Space Agency, and today I will present some nice study we published in 2023 regarding glacier, permafrost, and thermokarst interactions in mountain environments. So we made a very nice and detailed study on a single study site, and today you will discover this kind of complex environments that are still poorly understood. So the presentation is very classic. So I will introduce the subject, the study site. I will present very briefly the data and methods. I will expand a bit more on the results and then the discussions and conclusions. So I do need to remind you, but yeah, as you may know, high mountain environments are very important because at least 10% of the population depends on the resources, specifically on water resources. So this world water, it can be considered, as a world water tower, and there is a biodiversity hotspot in high mountain areas. And this is very good exemplified to the image at the right, because you can see a photograph of my town in La Paz in Bolivia. And you can see this dependency between people, human development, and the presence of a huge glacier Illimani, where we use the water for the city. So what is happening at global scale is almost all the glaciers around the world are losing masses. So the graph at left, you can see the glacial mass budget for 11 mountain regions from IPCC 2019. And you can see that the trend is decreasing. So all glaciers are losing mass. However, there is another important component of the mountain cryosphere, which is permafrost, mountain permafrost. And in this case, the permafrost is less studied. What we know about permafrost warming around the world is presented in the image at right. So this image represents the longest monitoring in Europe, based on more or less 10 or 12 sites. And beyond the internal variability, you can see that the trend is the warming. However, several mountain regions lacks of this information because it's very complicated to observe permafrost as this is a thermal state. We need some in situ measurements, and they are very challenging to study in mountain regions. However, the warming in the mountains is more pronounced at 0.3 degrees per decade. So this interaction between glacier retreat, permafrost warming are generating some mountain hazards on the context of climate change. So we can see more landslides related to permafrost warming. We can see glacier shrink very fast. We can see, again, mass movements related to glacier retreat. And one of the best examples, and the more recent one, is the Gulf of Sikkim in 2023. A mass on the lateral moraine has detached and has generated outburst flow. If you can see more, if you want to know about this study set, there is a very nice publication in Science from Satar et al. 2021. So for me, it's like more of the context of this of my project. So the study site of this presentation and the work what we carried out in 2020. So I will present the Chauvet glacial and periglacial complex, which is located in the southern French Alps. You can see a photograph of the very huge lake in 2008. And this study site is particularly important because at least 6 Gulfs occurred since 1930s. And as you can see in the video now, you can see that the water was falling into a glacial conduit, and the water was drained through this glacial conduit. So the main goal of this study and the publication was to explain which are the outburst flow origins. better understand the mechanism of these study sites and why the gloves has occurred 6 times at least. So in order to better understand what happened with this study site, we need to go back in time into the end of the Little Ice Age to provide a historical context. So this study set was covered by ice at the end of the Little Ice Age. As you can see here, this is a map of the état majeur coming from 1820, more or less at the end of the 19th century, and shows in blue the extent of the Chauvet glacial system, and in background you can see the pictures showing the ice. This is also evidenced by some photographs in 1988 and 1927, showing that at the background, Chauvet system was covered by ice. The first glove occurred in 1936. We don't have too much information about it, but what we know has been supported by some testimonies. The second glove occurred in 1966. We can see some traces in the photograph below. This is an extract of the photograph from 1966, and from where we can see some traces of material that has deposited in the first cone going forward into the valley. The third Orbus flood occurred in the 1970s. In this time, we can see some pictures about the event. We can see some cracks in the surface near to the frontal sector and some big lakes. We can also divine like ice falls below the debris layer. So all what we know of these gloves is the dryness time was 4 hours. The fourth glove occurred in 1991. We started to document better this kind of events. So the lake volume goes up to 50,000 cubic meters. And what we can see on the photographs is a huge crack in the surface, here in the photo A. We can see also the entrance of the glacial conduit, which has a diameter of 4 meters. We can also see some cracks after the drainage, and the development of the conduit is a bit complex below the debris layer. So we can see some extract of the photographs to look at. We have massive ice below the debris layer. The fifth glove occurred in 1997. This time we can see some traces of a big lake at the surface. Again, the entrance of the glacial conduit, and the glacial conduit developed below the debris layer becomes thinner and thinner when we approach the frontal sector. So this time the volume was 80,000 cubic meters with a drainage time of 3 hours. And the last and the most documented glove is in 2008, where we can see a huge lake at surface. We can see again the same context, and glacial conduit and entrance. This time was smaller. However, the big difference with this glove is the lake volume was 90,000 cubic meters with 60,000 cubic meters of sediment. So this was the main motivation to study this study site, because they had a long story about gloves, and all gloves are triggered more or less by the same triggering. Sorry. So what we use to use this study site, we use the huge aerial archive of French Alps, who goes back into the 50s until 2010, more or less, one flight every 10 years, from where we can see with a very detailed way the evolution of the surface. So we take several aerial flights, and we completed the time series using Pleiades high-resolution imagery, as well as UAV survey. So as this is the classic methodology used in cryosphere and geoscience, I will describe it very briefly. So all the flights has been processed with structure for motion photogrammetry, except for the Pleiades, but with the goal to produce DMs and orthomosaics. We use the co-registration steps to align the dataset into a single reference DM and shift all the images and all co-registered DMs. These allow us to compute surface elevation changes. And using orthoimagery, we compute free surface velocities using feature tracking offset techniques based on M0 pipeline software. Then we completed with some geophysics solving, more particular electrical resistivity tomograms, as well as induced polarization. And we also use geomorphological surveys to better understand the processes at surface. So very briefly, the basic measurement of geoelectrical resistivity involves 4 electrodes, usually metal rods, inserted into the surface, making a good electrical contact. An electrical current A is passed through the soil between 2 of the electrodes. As a result, an electrical potential difference V is measured between the other 2 electrodes. The voltage depends on the intensity of the current, the position of the electrodes, and the electrical resistivity of the soil, which quantifies more or less the ease of difficulty with which the current will flow. If resistivities beneath the surface is uniform, the current flow lines represented by the blue arrows in the animation resemble to the well-known dipolar magnetic field around a bar magnet. But if objects of different resistivity are present, they will distort the current flow and alter the measured voltage. So the current will tend to flow around more resistivity regions, like air-filled voids, the red sphere in the animation, and through more conductive regions, such as water-filled voids, the blue ball in the animation, thus increasing reducing the potential difference. To produce a picture of the electrical resistivity structure of the soil, we carried out numerous full electrode measurements at different locations and at different distance between the electrodes. You can see the animation in the picture. Most of the current flows close to the electrodes at different locations provide information on the resistivity, as well as the different positions, and the distance between the electrodes increases the current tend to flow deeper into the soil. So, what about what we do with all this data? First, we compute surface velocities. Here you can see a map of the average velocity of 50 years. The color bar represents velocities from 0 to 2 meters per year. And as you can see, the surface velocity is very heterogeneous. We can see some velocities up to 2 meters per year in the upper region and more weak velocities in the frontal sector. However, one interesting aspect to look at is in the central sector where the lake develops, the flow vectors converge towards the center. So I mean that the lake's evolution triggered the movement of the lateral landforms. If we look to the evolution of these velocities in time, so you can see in the graph below the evolution of the right side and the left side in the points that are located in the panel A, the green, red, blue, and brown. So the right side, show more homogeneous behavior, showing some accelerations and decelerations, but all within the uncertainties. So we can assume that there is a homogeneous behavior. However, the left side presents a more contrasted pattern. In this case, show an homogeneous velocities until 2000s, and then doubled in velocity after 2000s. This is concomitant with observations on rock glaciers and other frozen debris landforms, who also experience accelerations after 90s or 2000s. If we look to the surface thinning rates, you can also see very heterogeneous pattern. So the color bar represents in red high average thickness change in meter per year, and in blue some positive thickness changes. So again, the upper region, which is covered by a thin debris layer, present the more important thickness changes, as well as the lake sector, which is in the center. However, the other regions are more limited in thickness change. So when we look at the evolution of this time series of thickness changes, we can see that the right side, the thinning rates are very limited, below 50 centimeters per year. This is not the case for the left side, showing heterogeneous thinning rates, which are more pronounced close to the lake, which is quite normal because the ice melt in the thermokarst lake. So what is important to retain here is this heterogeneous pattern in a very small area. Regarding the results of the geophysical soundings, we carried out several profiles. The first one is a longitudinal profile of 1.5 kilometers with a 20 meters electrode spacing. Here I present the final results. You can see the surface of 1960 in cross and the surface on 2020 in dots. You can see the color scale showing in blue and dark blue, very resistive materials, in light blue, less resistive materials, and yellow and red, less resistive materials. So what is important here is we can identify on this longitudinal profile massive ice bodies in the upper region. We can see also in the after the lake layer of frozen debris with resistivity, with relatively low resistivities, and we could also identify the bedrock. If we look to the results of the transverse profile, we carried out 4 in order to better understand the internal structure along the Thalbeck on the study site. I will present only 2, the most important ones. The first is the profile number 4, which is close to near to the front, which shows very, very resistive landforms, very likely massive ice bodies. We can also identify thin debris layers at left side and a more thick debris layer at right. When we look to the profile number 2, we can see some more debris frozen layers above the surface with a more important debris coverage at the surface. However, what is important here is we can see some anomaly below the profile number 5, which is this less resistivity area within the frozen debris layers, which our interpretation is this is likely the entrance of the internal conduit. All these elements has been put together to better interpret the surface, the processes at the surface. So, helped to some geomorphological surveys, we could identify some glacial and periglacial landforms in the same hanging valley. So we could identify at right side A and B some periglacial landforms like rock glacier and back creeping push moraines. I will explain later the significance of that. We can also see a huge debris covered glacier from where the lake is developed, as well here in the sea zone, where we can see very important thinning rates. Here you can see the photograph from the Chambéron peak, which is the nearest one, and you can see the form of the V shape of the valley showing these complex landforms interacting together, and the lake in the middle connected to the Thalbeck and then the glacial conduit. So one of the main questions was how to explain the mechanism of the overflow. We know that there's a huge lake in late spring, but the lake is present through the year and every year, but they do not drain suddenly every year. So we identified 5 main causes. The first one is the hydrometeorological conditions, to represent snowpack, rain, etc. The second one is the closure and opening of the glacial conduit by creep. The third one is the thermal state. The fourth is the karstic network driven by geology. And the 5 is the topographic conditions. I will explain more detail these 2 because this is the more important ones. One element who called our attention during the study of this study set is the migration of the Talweg, who migrates every year in southward direction, with an exception of the last period in 2020, was the migration going in a northward direction. So this migration maybe is driven by the ice who melts below the debris layer, accompanied with the expansion of the lake. If we look more in detail on the P3 and P1 profiles, in the left you have the image of the entire study site. At the center you have the evolution of the surface on P3 and P1 profile, and at right you have a zoom on this small sector of the Talweg. So this profile shows the trend I explained before. The migration of the Talweg in southward direction, and suddenly in 2020, the migration in northward direction. This is more evident on profile 1, who presents more pronounced vertical and horizontal displacements. And on the last period, we can see the same pattern. So this suggests that the left side maybe has both sides play a role on the presence of the glacial conduit. However, it's interesting how we can explain the presence of this glacial conduit on this hanging valley. Because as we are in the middle between periglacial landforms and glacial landforms, it's not so common to see this kind of internal processes on mountain environments, at least on those debris covered glacier in the Himalayas that are very huge and large. So one possibility to explain the inglacial conduit could be very ancient water traces that can be observed here in the photograph on 1948. So the process is that these water traces have been covered by debris, and the water who erodes the ice becomes the glacial conduit more deeper and deeper and deeper, and then be trapped by debris, and then the water comes to melt the ice below the debris layers. This is also evident on huge debris covered glacier in the Himalayas, where more complex and sinuous glacial conduits has been observed and measured and quantified. If you want to know more about it, I'll let you look at Gulli et al. 2019, present a very detailed study. One other aspect that we can suspect about the presence of the glacial conduit is the thermal state. It's very curious because the glacial conduit is in the middle between periglacial landforms and glacial landforms. This is exemplified on the profile number 4 here, near to the front, from where we can see very resistive materials, and the Talweg and the glacial conduit is mostly located below the Talweg. We can also evidence the presence of the entrance in the profile number 2, again, in the middle between the two landforms. So we don't have temperature measurements. However, if we assume that the behavior of the structure is homogeneous, like very resistive materials of massive ice bodies at left and periglacial structure in at right, the thermal state may play a role on the position and the evolution of the glacial conduit. So, however, again, as we don't have a temperature temperature measurements evolution of this study site, we cannot get a very clear conclusion about it. So, I'm arriving at the end. So, in order, this multidisciplinary approach over 70 years of changes, combining surface velocity, thickness change, geophysical soundings, describe very detailed complex interactions between glacial and periglacial contexts. This kind of site you cannot find everywhere. So this thermokarst lake has developed in a context on all the elements play a role, starting from the topographical condition of the hanging valley. We are in the context of a dead ice body, from where the ice are they're not so dynamic, and the thermokarst lake from in the middle. Right now, the thermokarst lake has a capacity of 180,000 cubic meters, which is 2 times higher than the previous one in 2018. Although we have given some elements about the main triggers and the main drivers of the glacial conduit and the evolution of this study site, the always flow causes still remain unclear because we don't have enough data. So this is maybe an open door for people who do some modeling, because this kind of study sites could be also boarded from the modeling point of view and try to better understand the processes of melting ice, water availability, and thickness changes, etc. So, as the current of this lake capacity is very high, so we can also say that maybe in the near future we can have some new overflow on this study site. If you want to look more in detail and read more about all the hypotheses who take into account this paper, and if you want to read more about it, the paper has been published in 2023 in Earth Surface Process and Landforms journal. So please read it, and if you have some questions, don't hesitate to contact me. Thank you very much for your attention. It has been a pleasure for me to present my work to all of you. Thank you very much.
Thank you very much. It's always really nice to see geophysics used in these environments. So I don't know if anyone has a question that they would like to ask Diego. We usually ask people to either raise their hand or to indicate on the chat that they would like to ask a question, and then we get you to unmute and switch on your camera if you can in order to ask the question. So is there anyone with a question? Austin, would you like to go? If you can unmute yourself and switch on your camera, it's always much nicer. Thank you.
Yeah, can you hear me?
Yeah.
I just had a quick question about the resistivity results you got. What was the range of resistivities that you measured from the kind of the bedrock on one end to massive ice on the other?
What is the range about?
Yes, what was the range of the
About what?
resistivity?
Resistivity. Okay. I can go quickly to the presentation. So here's the one. Yeah. On the left side, we have like massive ice bodies around 1 million ohmmeters. On the right side, we have around 100,000 of meters. So yes, correspond more or less to the frozen debris layer.
Okay, gotcha. Thank you.
Are there any other questions? Tyler?
Yes. Okay, there we go. The video's on. Yeah, that was very cool presentation. Love all the pictures and the data. I have, I guess, a couple of quick questions, or one excitement that I was very excited to see your results showing the convergent velocities and the decreasing elevations kind of going along the locations of the thermokarst, because we got similar results in Wyoming. So I think near Yellowstone at Galena Creek, Wyoming. So that was really exciting to kind of see a similar process being measured. And then I have a question about the mechanisms and possible triggers of the floods. I was wondering if you've thought about like the distribution of the debris and the active layer thickness, whether there's like heterogeneity in the debris distribution, or if there's like subglacial till potentially leading to different locations that can be more favorable to the conduit. So that was just kind of floating on my head. Oh, and also I guess just one quick add-on to that is whether or not you've thought about having like imaging geophysics like GPR and radar or something like that. So yeah, thanks again.
Yeah. Thank you for your question. There's a very good question. I mean, we asked already this kind of uh, yeah. In the literature, you can find that the formation of glacial comets depends of a lot of triggers. Like the most important one in glaciers are temperature differences. So in this case, is maybe not the case in Glacier. Is maybe some we can suspect that it maybe play a role. However, from my point of view, the more important one is that the debris layer will isolate the ice from the surface. So you can open the glacial conduit by eroding the ice walls and by water erosion. However, when the glacial conduit comes bigger and bigger, the creep of the both sides will close it. So I have only qualitative elements to answer your question because I don't have too much data to do that. So is one another possibility is that the glacial conduit will be blocked by the collapse of the roof, and then the sediments come inside it and will block the water evacuation, and they generate the big lake, and then there is a history of difference of pressure and the that will do that collapse the glacial conduit. So there are still so many open questions about it that we cannot answer right now because we don't have enough data. So I don't know if I answered your question, your first question first. And the second one is that we didn't use GPR because it's a bit complicated on debris landforms. You have too many reflectors, but there is nothing possible. But at the time, we only think on ERT profiles because they allow us to confirm or discriminate on permafrost bodies, massive ice bodies, on frost and debris bodies. So there is some next perspective about GPR in order to better delineate bedrock. Yeah. This on the perspective.
Awesome. Yeah, thank you.
Thank you.
Diego, are there any sort of social implications of a flood that is twice as big as previous floods?
Yeah, good question. We analyzed the time series of rain, snow, and we didn't find a correlation about very rainy events or a huge snowpack accumulation. We didn't find a correlation. So it looks cyclic because the overflow comes every 10 years, more or less. But for now, there is no clear correlation. So, yeah, yes, a bit difficult to answer the question.
Thank you. Is there anyone else with a question for Diego? Well, I guess then it leaves me to say thank you very much for a really expansive presentation. This is an amazing data set. It's very rich. I'm sure there is a lot more to come out of this than you've talked about today. So thank you very much indeed.
Yeah, thank you to you.
So I think the next presentation is actually after Easter because we have EGU and various things like this. So keep your eyes out on the cryo list for the next seminar.
Yeah, thank you again, and I hope you enjoyed.
And thank you very much. And the presentation will be up on YouTube over the next few days. So thank you very much indeed.
Thank you to you guys. Hope to see you soon. Yeah, bye.